linear program approach to global attractors. So go ahead.
Okay. Thank you, Henrik. And first of all, thanks to the organizers for organizing this conference, and also to give me the chance to present the joint work with my supervisor, Milan Korda. Yes, and as Henrik said, it's going to be about the linear programming problem approach to global attractors. And yeah, I have to say there's not so much functional analysis coming here, but I hope I can at least give a small connection in the next slide here. So the idea, we will follow a similar idea than this idea here, how the parent Frobenius semi-group can be interpreted. I don't say that this is the way it should be interpreted, but at least this is one way of looking at it. So given a compact space X and a semi-flow on this set, then instead of considering or looking at the flow directly on the set X, what we can also do is we embed the space X first into the set of Borel measures on the space. So we have a natural choice for doing this. We can identify X with the Dirac delta in X. And to make this diagram commuting, here we have to use the push forward measure, and this induced by the flow, and this is exactly the parent Frobenius semi-group. So, and then the nice thing happens. So we start on our space X, embed to some measure space, and then we see that luckily everything works out nicely, and we end up with linear operators there. And something similar we'll also do here. And the final link is with the next example, where here we consider an optimization problem. So again, say we have a compact space X and a continuous function on this space, and this function we want to minimize. So let's start reformulating this minimization problem a little bit. So the action of g of x can be restated as the action of the Dirac delta acting on g. And since now this here is linear in the measure here, we can also take convex combinations and take a weak star closure. So this is the same as the optimization problem, minimizing the action of mu on g overall probability measures mu. And to restate this one more time, we just reformulate the condition of mu being a probability measure by being a non-negative measure with volume 1. And the cool thing here is the latter part here is now a linear programming problem on the space of measures. And of course, since here in between nothing big happened, we just reformulated. We cannot expect that the outcome here is much stronger. So we had to play with a much larger space for the linear structure that we gained. So very similar to the Koopman theory. And I hope at some point we can also apply at least some good methods to justify this approach here. So and whenever you have a linear programming problem, you like to look at the dual. So the dual has this form. We maximize the lower bound of g. Oops, here on x, this is missing. And yeah, of course, there is also not so much happening here. Of course, minimizing a function g is the same as maximizing the lower bound. So not much happened, and we of course see that there is no duality gap. So the optimal value of the primal problem is the same as the optimal value of the dual problem. But this concept we'll see later soon again. But now let's get to the setting we'll be working with here. Oh, oops. Oh, and I forgot. There's a small teaser. The non-negativity constraint here. Let's see what Jochen will say about this. We'll replace this by a sum of squares constraint. So this in the end will be a point where we will make use of the structure that we have. Okay, now to the setting. So we consider a compact constraint set in Rn. So this is the set we want to investigate our dynamics on, and we don't necessarily have to assume that it's positively invariant. And the dynamics are denoted by F and given by, and this is a locally Lipschitz vector field. We might even assume that it's globally Lipschitz because we're really only interested on the dynamics on X. So since X is compact and F is locally Lipschitz, it's Lipschitz on X, and we can just extend it to a globally Lipschitz function on Rn. Yeah, since we're only interested in the dynamics on X. And the flow is denoted by phi. So now we have everything to state what we need. Good. So on the first example, what did we do? We looked at the things that we are interested in and then embedded these via some identifying with a Dirac measure in this point. And we'll do something similar here. So for global attractors, we're interested in trajectories. So now we want to embed trajectories into a space of measures. So what we can do is looking at the so-called occupation measures. So for a given trajectory here, we can associate to this trajectory for a fixed initial condition the following measure that just integrates a function along this trajectory. And this is a nice object. The support of this measure is really just on the trajectory itself. But since we talk about global attractors, so we are interested in the long time behavior. So what we need here is infinite time horizon. And if we do this to guarantee well-definedness, we need some discounting factor. So for a trajectory with infinite time horizon, we do the same, but we discount with some factor here. So this is basically the Laplace transform of parent Frobenius group applied to the Dirac delta in zero. Okay, and what are some properties of those so obtained occupation measures? So first of all, what can we think of? So this occupation measure measures how much time a trajectory spends in the set A. So the measure of the set A is just the time the occupation measure spends, the trajectory spends in this set A. Further, it's non-negative, and a property that will be important later is that the support of this occupation measure is contained in X if and only if the trajectory stays in X for all positive times. And last point is, you could say it's a resolvent equation here. We have this, which is mostly called, in that case, the Liouville equation. And yeah, it's really not much happening because the occupation measure comes from a Laplace transform. So if we just add the definition here of the occupation measure and see that this part here is just a time derivative of v composed with the flow, and then apply integration by parts, we end up with the left-hand side. Okay, good. So on the next part, we will focus on this property, especially that it looks like those occupation measures, they capture information about which trajectories stay in the set X. And this is where it comes in, where it's useful to define the positively and maximum positively and negatively invariant sets. So these are all the points for which the trajectories stay in our constraint set for all positive, respectively negative times. Okay, and I haven't defined a global attractor yet, so this is what I will do, and I have to do because this is the main object in this talk. So the global attractor is the smallest compact set that uniformly attracts the maximum positively invariant set, which is denoted by m plus here. And the distance can be taken with respect to any norm in Rn. Choose your favorite one. Good. And luckily, those sets are related very nicely, namely by this classical theorem that says that the global attractor exists, is unique, and is given by the intersection of the maximum positively and maximum negatively invariant set. And those are exactly those points for which the trajectory exists for all real times and stays in the constraint set for all real times. Okay, so and since we have this, it's sufficient to identify the maximum positively invariant set, because then we can just apply this theorem and can find our global attractor. So this is our goal. Okay, and the good thing is we have already seen that occupation measures, they relate to properties of points staying in our constraint set. So let's extend this a little bit. So we're not interested just in one point staying in X, but we're interested in all points that stay in X for all positive times. So instead of fixing one initial condition, we now look at a distribution of initial conditions and take this as our starting point for the occupation measure. So for a given initial distribution mu0, we define the corresponding occupation measure. In the same way, we just average the occupation measure for a single initial condition according to the distribution mu0. Okay. And yeah, so in case of the initial condition given by the Dirac in some point, we end up with the previous case. Okay, so what are the properties here? So this is just a short reminder what we had before. Luckily we don't need to change much if we allow a bit more general distribution. So now the occupation measure measures the expected discounting time of the trajectory spent in A, and the occupation measure is again non-negative, and its support is contained in X if and only if for almost all points, mu almost all points, the trajectory stays in our set X. And yeah, at last also the Liouville equation holds with a quite natural formulation here. So this was the Liouville equation we had for a single initial value, which I just rephrased this here, shorted, and now we are in a situation where we can just easily replace the Dirac in X0 by our initial distribution and the occupation measure by the occupation measure we have according to this initial distribution, and the calculation is exactly the same. Good. Okay, so this allows us now to formulate an almost linear programming problem. So what do we want to do? We want to maximize the support of our initial measure, because we've seen that the support of the initial distribution contains information about the points that stay in X for all positive times, if it's a non-negative measure and if it satisfies the Liouville equation. And the first part here is the Liouville equation in positive time direction, and the second part here is the Liouville equation in negative time direction. So we link the maximum positively invariant set with the maximum negatively invariant set, and take the intersection, so to say, here, which by the classical theorem I've stated before really should give our global attractor. Okay. Yeah. So far this was a little bit heuristic, but in fact this is this problem here really gives the global attractor, but there is some problem still, because this cost function here is not linear. I mean, it's not even clear what a linear structure here on the sets should be like. So we have to apply some trick, and the trick is the following. So this was used by my supervisor when he investigated the maximum positively invariant set. So what do you do instead of maximizing the support? You can maximize the volume of the measure with the additional constraint that you bound your measure by the Lebesgue measure restricted to your constraint set. So what is the heuristics here? So you think one could think that an optimal measure here, solving this problem, is just the Lebesgue measure restricted to the global attractor, and defining mu plus and mu minus here as the corresponding occupation measures in forward and backward time direction. Yeah, so this already gives the first lemma. So the optimal value here is at least the Lebesgue measure of the global attractor. And how do we do this? Just as I just said, we choose the initial measure, the initial distribution to be the Lebesgue measure restricted to the global attractor, and define mu plus and mu minus as the corresponding occupation measures. But we will also see this is sharp. So this is the following theorem. So the optimal value here really is the Lebesgue measure of the global attractor. And yeah, now there are at least two ways to see this. One is to just apply a similar result on the maximum positively invariant set, once forward and once backwards in time, and you get there. And the argument there is that the Liouville equation is already strong enough so that any solution to the Liouville equation comes from discounted occupation measures. And this is a very nice argument, which in the end uses Ambrosio's superposition principle. But here we'll try to go a bit more, to present a bit more explicit approach. And to do so, we look at the dual problem. The dual problem is of this form, and by duality, we have that the dual problem is always an upper bound to the primal problem. So and further, as some structure of feasible points here, we see that functions v1 here, they're always non-negative on the maximum positively invariant set. Functions v2 that are feasible here are always non-negative on the maximum negatively invariant set. And together with this feasibility constraint here, we see that W is greater or equal than 1 on the global attractor. And this looks a bit technical, it's not so important yet, but the good thing is this allows us to create an outer approximation of the global attractor. Because by this condition, we see that the super level set of all points, or the set of all points where W is greater or equal to 1 will give, is a superset of the global attractor. And we'll later see that this superset gets tight when those feasible points get optimal. Okay, let's see how this goes. So the idea now is to find a minimizing sequence of feasible points for the dual problem, where the cost converges to the Lebesgue volume of the global attractor. And if we have found this, we've done a big step towards where we want to go, namely computing the volume of the global attractor and also getting outer approximations. And why is this? So the first inequality here we have already seen. We've seen that the primal problem is at least gives the Lebesgue measure of the global attractor. By weak duality, we have the second inequality, and by definition of the dual problem, we have the third inequality. And here, if we have found such a minimizing sequence with this property, then we see everything gets sandwiched by the volume of the global attractor, and we would arrive at the following theorem that says both the primal and the dual problem, they have as optimal value the volume of the global attractor, and further any minimizing sequence here gives rise to outer approximations of the global attractor, namely by those super level sets here, such that the outer approximation gets really tight. So it gets a precise up to Lebesgue measure 0 description of the global attractor. And luckily, this can be done explicitly, because we can find good solutions of this this constraint here that appeared in here in the dual problem, with nice enough properties, which allows us to define an easy minimizing sequence, for which we can see, that the corresponding function w, which is defined here, converges to the indicator function of the global attractor monotonously. So the cost will converge here. This cost will really converge to the volume of the global attractor. Good. Okay, so this gives the theorem, and at least that means that we have that there is a good way of finding outer approximations of global attractors, at least on the paper. But let's see how we can maybe do this by asking computers, for example. So how do we solve those problems? First, we're mostly interested in the dual problem, because only this gives outer approximations to the global attractor, but the problem is non-negativity constraints are hard to handle. So we'll use some additional structure. In that case, we want to talk about polynomials, because there we can borrow some positivity certificates from real algebra. Okay, so how does this work? So here again is our dual problem. And first step, we replace our function space that we are minimizing on. Here, C1 gets replaced by the space of polynomials. Good, step one. Next, we want to replace those non-negativity conditions. And this we do by very classic, I would say, classic candidates for non-negative functions, namely sums of squares. And here it looks like we somehow lost the information on the constraint set, but this is implicitly taken care of in those sum of squares. But I don't want to go into too much details here. But so we replaced non-negativity by being a sum of squares. But still, this is infinite dimensional, and computers don't like this so much. So what do we do in the next step? We just truncate the degree of our polynomials. So we take only polynomials up to degree k, and also the sum of squares are only of degree k of degree at most k. So this gives us now a finite dimensional optimization problem, and the cool thing here is it's convex. So we find global minima, and also this can be reformulated in a semi-definite program. So this has even additional cool structure, and there are also good solvers for it, at least at first. Yeah. Okay. So and then what we want to do? We hope that the sequence of optimization problems we've obtained, that this really does what we hope to do, namely that when the degree goes to infinity, we really get a solution, or approximate the solution of the original dual problem. So and this is the result stated here. So when the degree of those polynomials goes to infinity, then we really approach the optimal value of the dual problem, of which we know that this is the volume of the global attractor. And also, we still have this good property that a sequence of a minimizing sequence of solutions of those finite dimensional problems, they create outer approximations of the global attractor, and as the degree goes to infinity, those approximations get tight. And the main arguments here are the Stone-Weierstrass theorem that allows us to replace the set of continuous or C1 functions by polynomials, and Putina's Positivstellensatz allows us, or guarantees that it's really valid that we can replace non-negativity by a sum of squares constraint. Okay, and now I'm happy that I can show nice pictures. So what do we see here? This is the Lorentz attractor painted in black, and around this you see some red color here, and this is the outer approximation we've obtained by degree 8 polynomials. And I think this is already a nice picture. So I was happy when I could see it. And I have one last example. This is the NN map. It also has a strange attractor, and here the attractor is colored in red, and the approximation we obtained is colored in gray. And what I think is interesting about this picture is here we had to use polynomials up to degree 6, 8, and 10, and we just intersected their approximations, and it looked like, or we could see that only degree 10 polynomials, they discovered that here, this white part, that there should be, that the attractor is not there. So more complicated structure, I mean, it makes sense. More complicated structure means we have to work with higher degree polynomials, and I hope that this is a good example for this problem or for this interesting behavior. And by this, I want to conclude my talk, and thank you very much for attending this talk and having interest in it. Thank you.
Okay, so thank you very much for the interesting talk. Do you have questions? Jochen again.
I don't know what you mean by again. So, Corbinian, yes, you had this at the end where you replaced the C1 functions by the square polynomials. Yes. So I think I just missed something maybe, but why C1? Weren't you considering continuous functions before?
Yes. Yeah. Okay. So the dual problem looks like this. So those functions V, they are C1, and W may be continuous.
Okay.
But
thanks.
Yeah.
Other questions or remarks or?
Yes, maybe I have a very small question, a bit naive, but what is the limitation in terms of dimension of the system, since you are working with polynomials? I guess you cannot go with a very large dynamical system.
Yes. Yeah, I'm a bit torn, I have to say. What I really like is the application of where did I say it here? Putina's Positivstandsatz, because this is a really, really nice argument, and I think the functional analysis guy, the people, you would like it because it's proved using the spectral theorem, and so this is why I think I appreciate this approach, because it uses this nice argument, but also working with polynomials. I mean, if you're, as you said, Alex, if you're in high dimensions, then and if you consider polynomials up to degree 20 in dimension 5, this is already quite a bit. My computer, which is not very fast, it easily ran out of or ran into problems, I think, for.
And cannot you get rid of polynomials by considering other functions?
Yeah, there are also other classes where this works, but in a big point or an important point was reducing this non-negative. You would like to have a certificate for non-negativity, and real algebra provides some of these. So this is this Putina's Positivstandsatz, for example. And of course, other methods, I mean, even totally different methods work, because since we've shown that this problem here is precise. So if someone knows, I mean, there are also different techniques for solving such problems. So you can apply any technique to solve such problems. And yeah, the people in Toulouse, they're experts on polynomials. So it was at hand. Those good guys, they were just at hand to ask how it works. Yeah, so we used this. And for other function classes, I think those positivity constraints get more complicated. But thanks. Yeah, good point.